So when you assume that we are manipulating an object with the fingertip, we can just forget about the control of the hand. We can decouple it. So before we control the object, what do we want? Decide what we want to do with the object, and then we go to the torque control. This case, when you have not in fingertip control, so you have much less control at each force, at each contact force. For instance, here you have 3 contact forces but just 1 motor. Then you cannot decouple the 2 equations. You have to consider both together. Okay. Now, what really matters for the object dynamics is the Grasp matrix. Again, when you have an object with wherever, but we are considering these 3 contact forces, and you have lambda 1, lambda 2, and lambda 3, when you write the dynamics of this object, of course you have to consider the inertia components, that is the inertia of the object multiplied, that depends on the configuration variable of the object, the position of the object, times the acceleration, plus the Coriolis term, is equal to what? All these inertia and velocity, acceleration and velocity dependent components are equal to all the forces applied to the object. The forces applied to the object are of 2 natures. One are called contact forces, that is the one that you can control, okay? Plus the external one, the non-contact forces. It can be the gravity, it can be the collision with something, okay? So you have to decouple the forces that you can control plus the external forces like the gravity or some interaction with the environment. You cannot completely control, okay? So you have that the Grasp matrix multiplied by lambda, the Grasp matrix by lambda takes into account the control contact forces plus W, that is the external wrench. So W is a 6 by 1 vector that takes into account the forces component and the moment component. Okay? Where the moment comes from, so maybe you are writing everything in the object reference frame centered in the center of mass. When you apply a force at this point, an external force at this point, you have both a force and a moment generated by this force with respect to the center of the mass of the object. Okay? So if the force is not applied into the center, at the center of mass of the object, you always have a force and a moment. But you can also have moments directly applied. In general, you have this external wrench given by forces and moments applied onto the object. Even in this case, you have the dynamics version or just the static version when you are at the equilibrium. The equilibrium configuration simply has these components going to 0, and you have minus G lambda is equal W. Okay? Or minus G lambda is equal W plus the actual minus the component due to the dynamics. Okay? That can also be considered as an external disturbance, as an external force, because stays as a W. What I want to say here is that even if you consider the dynamics case or the equilibrium case, it does not change too much, provided that you know all the acceleration and velocity. Okay? Because you just consider like another W, which is the real external part plus the dynamics. Okay. So in this case, we can just focus on this equation, which is minus G lambda is equal double V, where you have that the double V is something that is external, that does not deal with your contacts, and can be, again, gravity, dynamics of the object, and while the G lambda parts takes into account the fact that you are applying forces at the contacts. So you have the object with the three contacts, okay? So you can generate the G, and the G lambda is the net force that is applied onto the object. Okay. So for given contact points, you know the grasp matrix. You know the double V, because it's the gravity or the dynamics that you want to do to the object, and you want to accelerate it, whatever, but you know. The question is how to choose lambda. So in general, in the control of the grasp, you have to choose the lambda vector. You have to choose the contact force. And you have to realize this contact force by controlling the torques of your hands. But you decouple things, no? So you want to now understand what to apply in terms of contact forces onto the object, and then someone will take care about applying it. Well, what to do here? What are the desired properties? Double V is given. In general, when you grasp something, you want to control any direction. For me, just consider the gravity. You know, I want to control, I want to keep holding the object for any gravity direction. Okay? Or if you consider the dynamic case, when in double V there is also the dynamic part of the equation, you want to accelerate it in any direction, okay, with respect to the power. Actually, I was wrong before because I was using the R. I want to accelerate in any direction with respect to the power, okay? So in general, you want to resist with the contact forces to any wrench that you apply. So one of the desired ability of the grasp is that, okay, I want to, the grasp must resist any external wrench double V, including or not the dynamic part. Okay? Well, this is now the case. Let's again coming back to our equation. So you have minus G lambda is equal double V, where your unknown is the lambda vector. Because this is given, the grasp matrix. It depends, once you have the contact points on the object, it's okay. The grasp matrix is given. Of course it changes if you change the grasp, but once the grasp is given, which is our case, the grasp matrix is okay. Is known. So lambda is the unknown vector. Double V is the known term. This is a linear equation, a linear system. Okay? In particular, is a linear system. This is a 6 by 9 matrix. This is a 6 by 1, and this is a 9 by 1 vector. Remember, because lambda was lambda 1, lambda 2, and lambda 3. Well, this is okay. So, from numerically, it's very simple because you have 6 equations in 9 variables. So we are happy. For sure, we can have some solution. But what we have to ensure is that the grasp matrix is full rank. I don't know if you remember the classical theorem of Cramer for a linear system is that you have, if you have a linear system, AX is equal B, okay, then there exists a solution only if the rank of A of the coefficient matrix is equal to the rank of matrix created by A and B, where you put B close to So if this is equal, then there exists a solution, at least a solution, which means that B should be in the column space of A, which means that B should be written as linear combination of the columns of A. This is the basic assumption. And to do this for any B, what we need to require? In our case, you know, we have G lambda is equal minus B. Minus double V. G is 6 by 9, this is 9 by 1, and this is 6 by 1. The only possibility is to have G full rank, full row rank. So if G has rank 6, even if also when you, for sure, whatever is double V is always can be expressed as a linear combination of the column of matrix G. So we need to require that the rank of G should be equal to 6, full rank. So under this case, we can say that we can resist any branch, or we can apply any branch. Resist or apply is okay. So if you change and put some dynamics here, you will apply something to move your object. Okay. So this is the first important part. This means that you can resist any branch. Well, there is something that we missed, no? Because this is okay, but we also need something, we are forgetting something, no? Because then I want to be sure that we didn't say before that lambda should be within the friction cone. So I want to satisfy this equation provided that lambda is within the friction cone. Because if lambda is not within the friction cone, we are in trouble. Okay? So now I have also to find a condition that allows me to say that I can solve G lambda is equal minus double V for any double V plus lambda is in the friction cone. Okay? Then I will just remember you that we are considering a single object, and you have one contact, two contact, three contact, and you have the friction here, the friction here, the friction here, and you want that your lambda 1, lambda 2, and lambda 3 that comes from the equation minus double V is equal G lambda should be within the friction cones. Okay. There are results on this that I can refer to in the notes, but for sure, if the grass matrix has a non-trivial null space, you can say, and there is at least 1/4 in the null space that belongs to the friction cones, then you can say that it's solvable in any case. So you need two conditions. One is that the null space of G is non-trivial, so is different from the trivial set of the zero vector only, plus that there is a lambda such that G lambda is equal to 0, which means that lambda belongs to the friction cones. Oh, sorry, belongs to the null space, and lambda E belongs to the friction cone, of contact E, where lambda E is equal lambda 1, 2, or 3 in our case. Okay. So we have this equation which is minus G lambda is equal double V, and we are facing with the problem of finding a lambda for a given double V and for a given set of points that defines the grass matrix G. How to do that? We are sure that we can do it because the rank of G is equal to 6, or the rank of G is equal to the rank of G and matrix V, more in vector double V, more in general. And also we are sure that the null space of G is different from 0, and there exists a lambda H homogeneous belonging to the null space of G and to the friction constraints. Okay? Now we have to find it. We have a kernel, so when you write minus G lambda is equal double V, then you have infinite solutions. Okay? And these infinite solutions are represented by this equation. So you have that lambda, you have to find lambda. So you have a lambda is equal to minus G pseudo inverse double V plus Ng zeta, where Ng is the base of the kernel of the grass matrix. Okay? So you have a particular solution. You have a particular solution that is given by the pseudo-inverse of the grass matrix plus infinite solution parameterized by a vector xi in the null space of G. If G has rank 6 and the lambda is a 9 by 1 vector, for sure the dimension of the kernel of the grass matrix is 3. So this vector has dimension 3 by 1, where 3 comes from 9 minus 6. Okay? So it's a three-dimensional vector. If this is true, if we are sure that there is at least one lambda h within the null space of G, then we can always choose. We have a theorem that says that for any, because this is given, right? For any double V, just pick the simplest inverse, pseudo-inverse matrix. This is a term that maybe is out of the kernel, is out of the friction cone, sorry, can be set to belong to the friction cone when for a certain zeta. So there always exists a zeta such that that solution is within the friction cone. For the case of two contacts, I can draw you for you this. So you have these two contacts. You have these two contacts here, okay? This is the gravity, okay? So this is in some sense the double V. You want to find the contact forces. You have the grass matrix. In this case, you have the grass matrix, double V is equal minus G lambda, okay? You have double V, you have G, you want to find lambda. Lambda is equal minus G pseudo inverse double V plus Ng zeta. In the planar case, remember, this is a three-dimensional vector because you have x, y forces in the plane plus torques in the plane. So the planar case, planar case. You have a 3 by 1 vector. Lambda 1 and lambda 2 are two-dimensional each because you have two forces here and two forces here in two dimensions. You can do normal and tangential force, normal and tangential force. So lambda is 4 by 1, right? Okay. And G is of course, is 3 by 4. So the null space of G is 1. So this zeta is 1 by 1. And what they represent? They represent the squeezing force. The null space simply represent the fact that you can squeeze the object. Okay? What is represented by G pseudo inverse W? In this case, it's very simple, because then you can have, if this is 2 of length, you can have 1 and 1 on this side, and this is the pseudo inverse solution. This is 2, and this is 1 and 1, okay? But for sure, this solution that you found coming only from the pseudo-inverse is completely out of the friction cone, because the friction cone is this. You have to stay in this green zone, and these two forces vector are out. Then you can complete this force by adding the null space. Okay, so you add these components such that the resultant one goes inside the friction cones. Okay, so if you zoom this one, if you zoom one contact, you have a friction cone that is green. You have your solution that is 1. Then you simply add the component in the null space of G, such that the overall force is inside the friction cone, and you can apply it. Now, here you can see the first idea, no? That the far you are from the friction cone, if you apply this force, you are far from the friction cone because of this length. Okay? If you apply more internal force, if you squeeze more, then this arrow arrives here, and this is the I don't know. This arrow arrives here, and this is the position of the overall force that you apply, and you are safer. So this solution, with respect to this other solution, let's say the green one, this one. This solution is safer than this, but you are expending more energy because you are pushing more. So it requires you more effort because you need to squeeze more. And you can also break the object, of course. Okay? So there is a trade-off between being far away from the friction violation constraint and not spending too much energy in pushing it. Okay.